In this lecture, we're going to discuss the Gaussian mixture model, which is another clustering algorithm. And before we get into that, why don't we differentiate between two types of clustering models. One is called soft clustering, which we'll focus on in this lecture, and the other is hard clustering, which we saw with k-means 2 lectures ago. So the hard clustering model that we discussed, k-means, goes like this. We're given data x1 through xn, where each point is in Rd, and we want to minimize an objective that looks like this, where we sum over each data point the squared distance to the cluster centroid that it was assigned to as encoded by the parameter ci. So xi is assigned to one of capital K clusters, and ci indexes what cluster that is. So we sum up the total number of squared distances, and that's our objective that we're trying to minimize. When we derived our algorithm for minimizing this, we saw how we could do a coordinate descent algorithm where we first update all the cluster assignment C, followed by an update of the cluster centroids mu. So when we updated C, what we did was for each data point, for example, the ith data point, we assigned that point to the cluster that it was closest to in the Euclidean sense. So that's what this is doing. Then when we allocate all of these data points to their nearest clusters, we update the cluster centroids by simply averaging. For the kth centroid, we average all of the data that was assigned to the kth cluster. This is an example of a hard clustering algorithm, and what we mean by that is when we're performing clustering and when the algorithm converges and outputs the final clustering, every single data point is assigned to only one cluster, and we don't have any sort of uncertainty. However, you could imagine that on the boundaries of these clusters, for example, a data point that could go either way, we might want to encode our uncertainty about the clustering of that data point with some sort of a weight, whereas the points that are right in the middle of the cluster we would want to be more confident about. So this leads to the concept of a soft clustering algorithm. Basically, a soft clustering algorithm takes the data and it breaks the data into clusters in some sort of an intelligent way. So for example, let's look at these plots where we have the raw data according to their clusters. So for example, all of the red points were generated from the same Gaussian. All of the green points were generated from a second Gaussian, and all of the blue points were generated from a third Gaussian. So the color is encoding which Gaussian that point came from. Now when we want to cluster these data points, what we see is this data set right here. So this is all we get to see. We don't get to see any sort of cluster assignments or what the cluster centroids are, etc. If we wanted to do a soft clustering of this data set, we might want to cluster it into 3 groups where we would get something like this. So the red points, red, green, and blue, again indicates which of the 3 clusters the data is assigned to, but these boundary cases are, in the context of k-means, this is something that's been considered, and it leads to an algorithm called weighted k-means. So we can take the k-means algorithm and make a simple modification to get a weighted k-means algorithm, which is turns k-means from a hard clustering to a soft clustering algorithm. So let's quickly review this algorithm before we move on to the Gaussian mixture model later. So with weighted k-means, what we have is this. We have, again, data x1 through xn, and we'll assume that the data is in Rd. Now our goal is to minimize an objective that looks like this, where we have still, for each data point I, a sum over each of the clusters, and we calculate the squared Euclidean distance of a data point to a cluster centroid. But now we divide that by a value beta that's positive, and we multiply it, instead of multiplying it by an indicator that says that xi was assigned to cluster K, we multiply it by a weight phi subscript I. So the subscript I is indicating the data point we're looking at, evaluated at k, which indicates the cluster we're considering. And these phi's now can be viewed as probability weights. So each value of phi I k is greater than 0, and the sum of them is equal to 1. And so in this case, we're breaking each data point up into different clusters according to how probable we think that cluster is in generating the data point we're looking at. The coordinate descent algorithm then gets modified in this way. So for a particular iteration, again, we look through each of our n data points, and instead of assigning them to each cluster, we assign responsibilities across the clusters according to this weight phi. So for the ith data point, if we want to know what is the responsibility of the kth cluster for generating the ith data point, or the probability if you want to think that way, it's equal to the exponential of minus 1 over beta times the squared Euclidean distance of xi to that centroid. We do that for each value of k, and then we normalize to get a probability weight. So clearly we've seen this type of a form before with the radial basis function for kernel models. If xi is very far away from a mu k, this value will be very small, and therefore the weight we assign to that cluster will be very tiny. And on the other end, if xi is close, relatively speaking, to the kth centroid, so this will be much smaller compared to the values for all the other clusters, and so this value will be much bigger relative to the other values evaluated at the other clusters, and so when we normalize, we'll get a high probability. So this is how we take proximity to the cluster centroids into account to break the responsibility for a given data point across the clusters according to how close that data point is to each cluster. Then when we update the cluster centroids, we have a weighted average now, where we take each data point. If we want to look at the kth centroid and update that vector, we look at each data point, we weight it by the probability of that point coming from the kth cluster, we sum that up, and then we divide by the sum of the probabilities. So you can imagine that if these phi's are pure indicators, meaning they're vectors of all zeros except for a 1 in the dimension indicating what cluster xi came from, that would correspond to a hard clustering algorithm, and we would simply be summing up all the points in the kth cluster and dividing by the total number of points. Now we are softening that by taking fractions of points and splitting them across clusters. So if we look at a plot like this, what soft k-means would do, for example, for a point like this, is say that we're going to say that the 0.75 fraction of this point is assigned to the green cluster, and a fraction 0.25 is assigned to the blue cluster. Whereas a point here would be entirely assigned to the blue cluster, and a point here might be entirely assigned to the red cluster. These border points are split across clusters to account for the fact that we're less certain about which cluster they come from. And then beta, as with the Gaussian kernel, defines what proximity means. What is a region? What does it mean to be close, and what does it mean to be far away? So this is now a parameter you would have to set using this algorithm. Let's now turn to a modeling framework called mixture models. With soft k-means, we took each data point and we, instead of assigning it to one and only one cluster, we broke that data point across clusters using a vector of weights, and we loosely used the term probability vector even though there were no probabilistic assumptions. So now we're going to look at a modeling framework where we do make these sorts of probabilistic assumptions by defining probability distributions. So specifically, if we want to distinguish between probabilistic versus non-probabilistic soft clustering models, we have this weight vector phi I. We interpreted it as being like a probability of xi being assigned to a particular cluster, Now we're going to do a mixture model where we explicitly define a prior distribution on the cluster assignment CI. So CI is now going to come back into our model, and we're going to define a probability distribution on it. And we also get a likelihood function of seeing the observation xi given the assignment of that observation to a particular cluster encoded in CI. So we're now using probabilistic definition to put these constraints on our parameters. Intuitively, something to keep in the back of your mind that we'll return to is the connection between the ideas of mixture modeling and the Bayes classifier that we discussed previously. And this will become more clear as we go on, but we can think of the class prior in the Bayes classifier model as now becoming a cluster prior. So it's the prior on a particular data point coming from a particular cluster, except this time now we don't know the label. Previously, the cluster, each cluster was like a class, and we knew the label for each observation, and therefore we knew which cluster it came from. Now we don't know that information. And similarly with the Bayes classifier, we had the class conditional distributions. So given what class it comes from, we have a specific class distribution on the data. Now we have cluster conditional distributions. So conditioned on a data point coming from a particular cluster, we have a specific distribution on that data point for that coming from that cluster. Before we define the math of the mixture model, let's look at some key features in a little bit more detail. So again, mixture models are a generative model, meaning that we're going to define a probability distribution on the data and then try to learn the parameters of that distribution. A mixture model is a weighted combination of simpler distributions. So for example, you can look up here where we have data in R2, and so we want to learn a distribution on R2, and the third dimension corresponds to the density at a given point in R2. And we construct this complex density of these three humps here by taking a weighted combination of three simpler distributions. So these three distributions are actually three different Gaussian distributions with different means and different covariances. So we have three simple distributions, three simple multivariate Gaussian distributions, and then we weight each of those and put them together according to a probability of a particular Gaussian to get our final density. So from a distribution like this, we could get a data set that looks like this, where this view is simply looking straight down on this density, and we get a cluster here corresponding to these points, a cluster here corresponding to these points, and another cluster here corresponding to these points. So this is the data that we're actually going to be given, and now we want to propose a Gaussian mixture model and then learn the resulting means and covariances and mixing weights on those three different Gaussians. To define a mixture model, we have to define a generative process. So this is the same story with all Bayesian models. If we want to define what it's doing, we have to hypothesize how the data is generated from that model. So here's the generative model for a mixture model. We again have data x1 through xn, where each x is in some space. It could actually be a complicated space, so we'll be abstract at the beginning, but you can also think of the space as just being Rd. We have model parameters for the mixture model, which include, for all mixture models, will include a k-dimensional probability distribution on k different clusters. So if we assume there are k clusters, we have a k-dimensional probability distribution on each of those clusters. And also parameters for each cluster. So theta 1 would be the parameters for the first cluster up through theta k, which are the parameters for the kth cluster. The generative process, so the process for generating data from this model looks like this, where for each observation, we first generate a cluster assignment using a discrete distribution with the parameter pi. And that is IID, so every single data point we're going to assume is generated independently and with the same discrete pi distribution, meaning that the probability that we assign any particular data point to the kth cluster given pi is equal to pi k. So this is the prior. Then, given the cluster assignment, we generate the actual observation, xi, from some probability distribution on x, where the parameter that we use for that probability distribution is picked out by the indicator ci. So let's make some observations right away about this generative process. First, we see that each data point a priori, we're assuming, is generated, is first assigned to a cluster. Before we see the data point, we have to first assign the data point to a cluster according to pi. Then, when we assign it to the cluster, we pick the parameter to generate the data point according to the indexing of the cluster. And so we use the same exact probability distribution. So we're going to assume that p is the same for all clusters. So it's, for example, a multivariate Gaussian or something more complicated than that. The only thing that's differing across clusters is what parameter we use for that cluster. So if p is a multivariate Gaussian, then theta would be the mean and the covariance for each of those k Gaussians. Also, notice that if 2 points, xi and xj, are assigned to the same cluster, then their values ci and cj are equal to each other. And in that sense, we're assuming that xi and xj both have the same, are generated from the same probability distribution. So they're clustered together by the fact that they share the same parameters to their data generating distribution. So we can come back now to this picture for the Gaussian setting to see the impact of the weights only. So in these two Gaussians, we have the same Gaussians, but we change the weights. And so what we have is, for example, something that looks like this if we have uniform mixing weights and we get a data set like this. And if we change the weights, so for example, this cluster gets more probability, then we can get something like this, so where we have more data from one cluster than from another, as opposed to even weights, in which case they're equally probable. So the Gaussians define the region, and the weights define how dense the data is in each region.